drill into this and say that this is our reservoir, we're going to have difficulty really getting much production online without stimulation. And if we want to stimulate it, we might decide that we need to hydrofrac the system. We might need to go into an acid treatment to try to enhance some of the porosity nearby. But we've got a relatively low porosity here. But now let's add, and Steve, I'm going to do something odd. Let's come out here, and now we're going to add fractures. And we have sort of a random distribution of fractures. They're not communicating very well. Depending on what the fracture aperture and the average length, then we want to think about what is the relative spacing between them, or we can express this as a fracture density. How many fractures do we have per unit volume in the rock? We want to think about their connection, and we want to think about something called transmissivity. What can happen is if we have these fractures, they can greatly enhance the porosity. A fracture system, depending on how complex, how many fractures, might bring porosity up to 5%, maybe even as high as 10% porosity in the system. And so we can enhance the porosity in the system. If we look at this, we have an overall anisotropy here. We have more fractures that are along this orientation than are along this orientation. And so as we start testing this, we might perceive that we have some permeability anisotropy in the system. It's not uniform permeability in our system. And so what will happen is the geologist, the geophysicist, the petrophysicist, the person who interprets the logs and does the calculations off the logs, and the engineers will get together and say, okay, we think we have a reservoir here. Right now it's not behaving in a way that is economic. Can we enhance? And so they would decide whether or not they were going to come in and try to stimulate this with a hydrofrac. When you do a what do you guys know about hydrofracs?
You basically pump water into it to try to break it open.
The fundamental idea of hydrofrac is that if we have a borehole here, this is going to be, now, the real size is going to be something like this. We've drilled the well, we've logged it, we've carefully analyzed the logs, you've had a geologist look at the logs, you've had a physicist look at the logs, the engineers have examined the logs to look at the system and decide, am I going to set casing or not? So that's the first stage of decision. Once the logs have run, have been interpreted, you're going to sit together either, now it's electronically, in the olden days it used to be actually sitting at a table together with the paper logs. Now everything's done electronically. My daughter is in the oil and gas industry, and there was one weekend about a year ago, she called up and said, I'm sitting on my 5th well. This is really cool stuff. And I went, wow, cool, where are you? I'm in my apartment. She was doing everything via computer. And so she had called TD via the computer. She was looking at the log suites coming out via the computer. She was conversing back and forth with the engineer, with the tool pusher on site, the company man on site, deciding, do we set casing? If we set casing, do we perf? And so what you typically do is you're going to set in here casing inside. going to cement this and try to get as good a bond as possible with a cement that is intended for this particular application and is appropriate for the type of material, for the depth, for the pressures that you see, for the temperatures that you see in this system. So that now we have an open hole with tubing, and we decide, okay, we're going to perf. When we perf, we run a tool down, and the tool is usually a smaller diameter cylinder that has directional charges mounted in that. So they bring the tool down, they orient it appropriately, and in this case, what we would do is we would orient probably east-west rather than north-south. It's going to be an engineering decision, but since our anisotropy is east-west, we're probably going to orient this thing east-west to try to get these fractures to start to connect up in the system. So then we set in a shape charge, and effectively you blast a series of holes into the casing that reaches through. These holes will penetrate out into the formation. And you choose how many shots you're going to have. Is this 10 shots? Is this 20 shots? So the next stage you have to start thinking about is, what is my depth? Because our confining pressure, just the confining pressure of the system in the most general sense, is going to be rho GZ. What's the density of the material above on average gravitational system depth? And so this is density, gravity, depth. And you're going to get some indication of what should the most likely formation pressure be. So that you want to start thinking about how much energy do I need in order to be able to propagate a fracture. We want to think about the material. And we're going to think about something called the crack toughness. How difficult is that material to fracture? Is this a really brittle material that fractures easily? Is this a brittle material that is incredibly strong? So that's going to tell us how much internal pressure I need.
Would you also look to see if the material is more elastic, like mud?
Well, you would look at it in terms of, here we would look at the material and we're treating it as, in the most simplistic case, an elastic material. But in reality, we're thinking of it as a poroelastic material because we're going to have fluid bleed, we're going to have pressure drop off. So we want to know what sort of internal pressure do we need to start the fractures and to propagate the fracture far enough. Now, we're going to have mitigating things that we need to worry about. You know, let's say this is our lease. Now, here, if that is our lease, we don't want to propagate the fractures this way because we're going to go off the lease and we're going to run into problems with the corporation commission. We're going to run into problems with these operators. And so we would only want to go this way. And depending on what the scale is, we would want to propagate that fracture for a certain distance. So you have to think about what is the crack toughness. There is an intriguing BO crack toughness equation that we can use to start thinking about that. And you determine how much fluid do I need? What does the fluid need to be? Does this need to be slick water? What sort of amendments do I need? What sort of proppants do I need in order to cause these fractures to link up? You're going to then set a packer in here, which is effectively a rubber donut that seals off that, bring the pumps on, have enough fluid on hand to force the fluid into this, increase this pressure to the point that it will allow these to propagate out. And they will propagate out as a near vertical plumose feature, and the engineer operating it is really an artist. It's astonishing when you go out on a hydrofrac job, because they effectively have a little joystick, but they're playing with the pressure. And the engineer, if they're a good engineer, they're seasoned, they can feel the fracture propagating. And so they can sit there and bump it and bump it and bump it and go, okay, yeah, okay, that's it, we're done. They really have this down to a very, very fine art as they try to get these fractures to now communicate up and link, so that now we have through-going fracture. In here, we can pull back whatever fluids we can recover and then start production. Yeah?
Anastropy, how do you say that?
Anisotropy.
Anisotropy.
A material that is isotropic has the same basic material properties in all directions. A material that is anisotropic will have differing material properties in each direction. And we typically will express it as a XYZ or as a 1, 2, 3 coordinate system for looking at the anisotropy. And then that anisotropy is actually a tensor property. It's ellipsoidal in nature.
Do you think is it easier to start fracture as we going right down, or?
Well, this would apply whether we're dealing with a horizontal lateral or whether we're doing a vertical. Because if we have a horizontal lateral, let's say that we decide we're going to whipstock off and come out and try to get as much of the production as possible in that system. So if we drilled a well, let's say we drill our master here, then as we drill the lateral out for production purposes, depending on how much you want to invest and depending on what sort of technology you have on site, you might drill up to 8 laterals from that. And then you really have to think about, if I have existing anisotropy, for example, do I really want to invest in fracking this lateral? Is it even wise to drill that lateral? That's a decision that has to be made with the geophysicist, with the petroleum engineers, with the geologist at hand. This one would be a good one to frack because it is going to be perpendicular, and then you would set a series of stages where you would frack, back off, frack, back off, frack, back off, and depends on how you set this up. Sometimes you try to frack a multi-stage all at once, that's expensive. Or you try to stage your fracks here. But the main thing you're trying to do is to extend the fractures. You're trying to cause these fractures to link up so that they're better connected. You're trying to prop them open so that they stay open, so that you have good transmissivity in the system, so that you can get back as much of the fluid that you injected as possible. It's impossible to get it all out. In fact, most of the time your recovery is not so great. And then start producing the hydrocarbon in that particular system. Does that make sense? So the mechanics, the physical mechanics here is the same whether you're dealing with laterals that are vertical or a borehole that's vertical or laterals that are horizontal. The actual operations are quite different depending on whether you're dealing with these horizontal laterals or these verticals. Tim?
Could you go into more detail? You mentioned a poroelastic material.
Poroelastic. The easiest way, and Tim, this is going to be rather simplistic.
Okay.
The easiest way to think about it is, let's just imagine that I have a semi-infinite material here that is a plate. So I'm going to have a hole here. I'm going to then perf and try to drive a fracture out this way as a mode 1 flaw. Now, if this has 0 porosity, it is completely impermeable to any fluid at all, then this will simply drive out, and I can manipulate this flaw by controlling my internal pressure versus whatever external pressures I have in the system. I'm not going to lose any I'm not going to leak. But if this is a porous material, keep in mind this pressure is higher than the fluid pressure, higher than the formation pressure. And so I will develop a, oh, blue, perfect. I will develop a halo of fluid that has migrated away from this particular system. It leaks. And so this would be representative of the volume of fluid that I have lost into the formation, because it's a porous material and I'm operating at higher pressure than the pore pressure of the fluid. And so that's the volume that I've lost in the system. So that then drops my internal pressure. If I'm the engineer sitting up on top trying to drive this thing, so I work for Halliburton, and I've got these pumps that are just about as big as this room, and I'm trying to drive this thing, I feel how much am I losing to the formation? Am I causing formation damage? All these different thoughts are going through the engineer's head as they're trying to drive this fracture to enhance the recovery in the system. Does that make sense? Does that answer your question?
I guess I was just wondering so that's the poroelastic material.
That would, a poroelastic material would be a material that behaves on the large scale as an elastic. So it's a brittle elastic, but it will take your fluid, which is your driver for this particular flaw. And so you lose pressure as you leak off in the system. Okay? Does that address?
Yes, thank you.
All right. So what we've done is so far we've been thinking about fractures as these flaws that develop in a material. They tell us, that's gross, they tell us information about the tectonic and structural history of an area. We've learned that we see different patterns depending on the type of structural system that we're dealing with. We talked a little bit about the modes of fracture, and we kept a fairly simple fracture modes where we imagined a flaw here. This flaw, if we try to propagate it doing pure tension, this would be a mode 1 flaw, and it would tend to propagate as a straight plane. If we think about instead trying to propagate by taking this material and forcing this side this direction, pulling this side this direction, what will happen is that the flaw will curve. The fracture will actually curve on us in that particular system. This is a mode 2. And then if we had the Superman tearing a phone book mode, so that what we're doing here is we're trying to take this a mode 3 is where I take this and tear it. That is a mode 3 type of a system. And what we left out was that in this case, we end up with an en echelon pattern in the tip line of that flaw. We can have mixed modes. a mixed mode flaw, you can have mixed mode 1 plus 2, 1 plus 3, 2 plus 3, 1 plus 2 plus 3, depending on what's going on in the near field of that propagating fracture and the far field of that propagating fracture. When we think about these fractures and how they're going to develop in a system, we want to think about this, at least get this into our heads, that we're really just playing with energy. If we have here a system like this, if I am going to form a fracture, what must happen? Well, I have to cause the material to break. So what we do is we have loss of cohesion. What we're doing is we're breaking the material, and we're breaking it at crystal boundaries, or we're actually breaking across a crystal. So if we go back to mineralogy, remember physical geology, Dr. Cornell spent a bit of time talking about minerals, mineral systems, different classes of minerals. You played with minerals in the lab so that you know that this is a three-dimensional network here of silica. These require different energies. Some materials here might be a little bit more ductile than others, and so these fractures can behave as perfectly brittle materials, and in that case we just have to worry about the Biot's characterization of crack toughness for propagating through the material. If we're breaking minerals, or we're breaking crystal lattices, then we have to think about, well, is it behaving brittly? Is it behaving as a brittle ductile material? Is it behaving as a ductile brittle material? Is it behaving as a ductile material? Each one will burn a different amount of energy in the system. So if we think about trying to propagate a flaw in a system, so I'm going to make a flaw here, and I want to make this flaw propagate. I have to add energy into that system. The ability to propagate that flaw will depend on the strength of the material, on the type of material. If this were a plastic material, it would have been more difficult to cause that flaw to propagate. This is paper. What if this was stainless 404 steel? It would have been a lot more difficult to get that particular flaw to propagate in that system. Because what's happening is that right here, the easiest way to think about it we're creating new surface area at that point. Now, let's go back to chemistry. If you remember, Mr. Simcox or Dr. Purser up there in chemistry talking about surface free energy, Gibbs free energy, the energy within a system, we're changing the energy state of this system. We're taking bonds that were happy here, and we're now exposing them at a free surface. They're not happy. any longer. We're changing the energy state in that particular system. So we want to think about what is the cost. We also want to think about what's happening and that's just gross. What is happening at what we call the crack tip process zone. So here we're going to look at what's happening just right there. That crack tip process zone. If we think about this in really kind of a simplistic view, what's happening is I'm concentrating stress here. I'm enhancing the stress field by quite a bit. So the things that can happen is I can deform brittly, just this one fracture and zoom, it propagates out. I can cause a zone of plastic deformation so that this would be a zone of plastic yield before the flaw propagates. So that's going to burn up some energy, and the flaw won't propagate as far in the system. I can, instead of having plastic deformation, I can end up with, and it's drawn a little bit differently, a zone of microcracking, where the material's trying to break, but we're not at the right orientation. Maybe we don't have enough energy, and so it just gets all these little bitty cracks in the system before it finally propagates. And so there's been a lot of research about what's happening at that crack tip process zone to try to understand how far will these fractures propagate, because depending on how much energy we put into the system, plus what's the material type, what's the depth, yada, 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 that fracture might propagate for a great distance, or it might not go very far at all. So when you look at the fracture densities that you have in these systems, you really want to think about what was the energy input, what sort of structure tectonic system did I have, and how are these fractures expressing that?
Would it be safe to say that based on that with the zone of plastic yield, because it does give that if you had a much harder brittle something, you would get a further propagation versus something that's softer? It's good.
Depends on how tough the material is.
Okay, so there's a.
It depends on that crack toughness. But yes, in general, if it is brittle, it will tend to propagate further than if it is more ductile. But there are certain materials that are brittle but are incredibly tough. So it's difficult to cause those fractures to really propagate. And so it's going to depend on the type of material. It's going to depend if we're dealing with a subsurface system. You know, if you're in a shale clay, you have a very different game than if you're in a carbonate or a sandstone clay when you're trying to hyperform. Okay? All right. Now, that's basically it for fractures. Woohoo! We have a quiz. I know you were waiting.